Have you ever imagined swimming or sailing over mountains? Not in a science fiction movie, not in an unrealistic dream, but in the real world with real ships, real rivers, and real mountains. What once seemed impossible has now become a tangible reality, and it is happening in China. In the modern world, such an achievement is only possible thanks to extremely complex hydraulic infrastructure, dams, hydroelectric power plants, and artificial navigation systems capable of overcoming staggering differences in elevation. And when it comes to hydropower, no country rivals China. In the modern world, such a feat is achievable only through extremely complex hydraulic infrastructure, dams, hydroelectric power plants, and artificial navigation systems capable of overcoming dramatic differences in elevation. And when it comes to hydropower, no country matches China. On its own, the People's Republic of China produces approximately one-third of the world's total hydroelectric power, with nearly 391 gigawatts installed out of about 360 gigawatts generated worldwide. This leadership is not the result of chance. The country is home to some of the most colossal hydroelectric installations ever built. The Three Gorges Dam, for example, remains the largest hydroelectric power station in the world, with an installed capacity of 22.5 gigawatts. Other giants, such as the Goupitan Dam, also occupy top positions in global rankings. In fact, the 5 largest hydroelectric power plants on the planet are all located in China. But beyond energy production, these titanic structures fulfill another essential function. They redefine river transportation. In certain mountainous regions of the country, Chinese engineers have succeeded in doing what once seemed unimaginable, allowing ships to cross entire mountains by literally lifting them into the air using giant elevators. Today, we are going to discover how China achieved this remarkable technological feat and how boats can now fly over mountains. To understand how China made navigation over mountains possible, one must first grasp the scale of its dominance in the field of hydropower. No other country has invested as many resources, as much time, and as much technical expertise into large-scale hydraulic energy development. On a global scale, China alone accounts for roughly one-third of the world's installed hydropower capacity. This dominant position can be explained by a unique combination of factors: a geography rich in powerful rivers, a frequently mountainous topography, rapid economic growth, and a national energy strategy clearly oriented toward renewable sources. In this context, dams are not merely electricity-generating facilities, but true pillars of territorial development. The Three Gorges Dam perfectly illustrates this ambition. With an installed capacity of 22.5 gigawatts, it remains the largest hydroelectric power station in the world. But it is far from an isolated case. The Goupitan Dam, though slightly smaller, ranks second globally. Even more striking, the 5 largest hydroelectric power plants on Earth are all located in China, a fact unprecedented in the history of energy engineering. However, these colossal infrastructures serve far more than a purely energy-related function. By retaining the waters of major rivers, they profoundly alter river ecosystems and create sometimes extreme differences in water levels. Where water accumulates upstream, rivers become deeper and calmer. Downstream water levels can drop abruptly. These transformations pose a major challenge for inland navigation, particularly in mountainous regions. Yet China cannot afford to sacrifice river transport. Inland waterways are among the most efficient and energy-saving means of moving goods and passengers over long distances. As a result, every new dam raises a crucial question: how can the continuity of river traffic be maintained while fully exploiting hydroelectric potential? It was precisely this dilemma that led Chinese engineers to design radical solutions, pushing the limits of conventional engineering. In some regions, simple navigation locks are no longer sufficient. Entirely new systems had to be invented, systems capable of lifting entire ships to heights equivalent to buildings dozens of stories tall. Near the Goupitan Dam, located in the mountainous province of Guizhou, science fiction seems to have taken physical form. Here, river navigation does not stop at the mountains, it crosses them. A vessel slowly approaches a massive structure that looks more like an industrial building than a traditional port facility. Guided by an artificial channel, it enters the structure. What happens next defies intuition. Inside the structure lies a device of astonishing complexity, a system of lifting cables, 2 rows of drums, mechanical reducers, and drive mechanisms installed on both sides. In essence, it is an elevator not for people but for entire ships. To someone accustomed to residential buildings, the immense scale and apparent slowness of the mechanism might seem excessive. Yet it is precisely this design that makes the system both effective and safe. According to the engineers in charge of the project, this elevator is capable of lifting or lowering a 500-ton vessel in approximately 10 minutes. In other words, a standard passenger ship can literally rise into the air in a surprisingly short period of time. And 500 tons is merely a typical load. The system's maximum capacity reaches approximately 800 tons. In this case, the lifting time is longer, but the experience remains just as spectacular. The height to which a ship can be lifted is equally remarkable. Depending on the water level and the river's flow rate, the elevator raises vessels to a height ranging between 236 and 259 feet. This corresponds roughly to the height of a 26-story building. Finding oneself at such an altitude aboard a ship surrounded by mountains is an experience that fully justifies the system's reputation as a true engineering feat. Some may argue that ship elevators have existed for a long time and therefore do not represent a truly radical innovation. But this criticism overlooks a fundamental detail at Goupitan. There is not just a single elevator. The system includes 3 ship elevators operating in series. After passing through the first elevator, the vessel is guided toward a second one, which lifts it even higher. Each of these elevators operates according to the same principle. The ship enters a water-filled chamber, the system is activated, and the entire assembly vessel and basin together rises as a single unit. This approach reduces structural stress and ensures maximum stability during vertical movement. Thanks to this succession of elevators, river navigation reaches places where topography once made it impossible. The first ship elevator in the Goupitan system is only the beginning of an extraordinary vertical journey. After completing this first stage, the vessel is directed toward a second elevator designed according to the same technical principles, but intended to raise the navigation level even further. On its own, this second device lifts the ship by several additional hundreds of feet. In total, after passing through the first 2 elevators, the vessel reaches a cumulative altitude of approximately 653 feet above its starting point. This height is difficult to comprehend without comparison. It is roughly equivalent to the height of a 66-story building. If the Great Pyramid of Giza stood nearby, the ship would easily tower above its summit, the pyramid reaching about 456 feet. As for the Statue of Liberty at 305 feet, it would appear almost modest in comparison to such an elevation. Once these 2 ascents are completed, navigation must still overcome a final challenge, descending to reach the body of water located behind the dam. To achieve this, the system includes a third elevator installed at the end of the mountainous navigation route. This elevator lowers ships by a height that can reach up to 154 feet, a value that varies depending on river levels and hydrological conditions. At first glance, such a system may appear inefficient in terms of throughput. Unlike a natural river where multiple vessels can move simultaneously while simply maintaining a safe distance, a ship elevator transports only one vessel at a time. This limitation is undeniable. However, it is not as restrictive as it might initially seem. Engineers have optimized the entire route in order to reduce waiting times. While one vessel is passing through the first elevator, another can already be positioning itself upstream, ready to be lifted in turn. In this way, a true navigation chain is established, allowing a nearly continuous flow of ships through the system. Admittedly, this does not match the freedom of natural river navigation, but given the extreme topographical constraints, it represents a remarkably effective compromise. Ultimately, this 3-elevator system transforms an otherwise impassable mountain barrier into a navigable corridor, once again demonstrating the ability of modern engineering to push beyond the limits imposed by geography. As impressive as the ship elevators of the Goupitan system are, they represent only part of the equation. Between these monumental vertical structures lie distances that must also be traversed. Moving ships from one elevator to another through mountainous terrain presents an engineering challenge just as complex as the lifting process itself. In most cases, when managing elevation differences along navigable waterways, traditional locks are used. These systems allow vessels to rise or descend gradually without ever leaving the riverbed. At Goupitan, however, this solution was simply insufficient. The river was not originally designed to accommodate such a system, and the surrounding topography imposed far more severe constraints. Chinese engineers were therefore forced to imagine a radically different solution. The main section connecting the elevators consists of an open aqueduct, literally suspended along the mountainsides. Although aqueducts are not a modern invention, ancient civilizations, particularly the Romans, built them centuries ago. Integrating such structures into an environment this rugged and in direct interaction with giant ship elevators represents an unprecedented challenge. But the route is not limited to aerial structures. Part of the navigable waterway passes directly through the mountain itself. To achieve this, China relied on its exceptional expertise in tunnel construction. Today, the country is one of the world's leaders in the use of massive tunnel boring machines capable of carving large diameter passages through extremely hard rock. Thanks to this combination of open aqueducts and tunnels carved into the heart of the mountain, engineers created a continuous navigable route approximately 1.4 miles long. This infrastructure seamlessly links the various ship elevators and allows vessels to cross terrain that would once have made navigation impossible. Such a system is obviously not inexpensive. The construction of the dam and its associated infrastructure, carried out between 2003 and 2009, required considerable investment. Nevertheless, the result stands as a striking demonstration of modern engineering's ability to reshape the natural landscape in order to meet strategic energy and logistical needs. Faced with a system of such complexity, a natural question arises: why invest so much effort, time, and financial resources into an infrastructure this costly, especially when the dam itself is not among the most powerful in the country? To answer this, one must closely examine the geographical and energy context of the region. The Goupitan Dam is located in Guizhou Province at the heart of the Yunnan-Guizhou Plateau. This region is characterized by an average elevation of around 100 meters and by extremely rugged terrain, approximately 92% of its territory consists of mountains and hills, a landscape largely unsuitable for traditional transportation infrastructure, such as highways or high-capacity rail lines. Yet it is precisely in these mountainous areas that numerous rivers with strong energy potential flow. In such an environment, the construction of a dam almost inevitably leads to major consequences for river navigation. Any reservoir creates a difference in water level between upstream and downstream. In some cases, this difference is moderate and can be managed using conventional locks. At Goupitan, however, the drop in water level downstream of the dam is so significant that a system of locks, even one with multiple stages, would have been extremely slow, risky, and unreliable for large vessels. As a result, engineers had to abandon conventional solutions. A single ship elevator would also have posed problems, both in terms of operating time and mechanical safety. It was this exceptional constraint that led to the adoption of a three-elevator system capable of distributing loads and managing level differences that would otherwise be unmanageable. But the question remains, was it really necessary to build a dam at this location? From an energy perspective, the answer is clearly yes. Guizhou's hydropower potential is estimated at approximately 18.7 million kilowatts, ranking the province sixth nationwide. On the Wu River alone, there are already 8 hydroelectric power stations with a combined installed capacity of nearly 8,500 megawatts. Goupitan is only one link in this chain, but a strategically important one. This development is part of a broader national policy. China seeks to maximize the use of its hydraulic resources in order to reduce its dependence on fossil fuels. By the 2030-2035 horizon, renewable energy sources are expected to account for a major share of the national energy mix. In a region as mountainous as Guizhou, hydropower emerges as the most logical and efficient solution, even if it means literally making ships navigate over mountains. Beyond technical and energy considerations, the ship elevator system at Goupitan plays a fundamental role in both the regional and national economy. To understand its importance, the Wu River must be placed within the broader context of China's vast hydrographic network. The Wu River is a major tributary of the Yangtze River, the longest river in Eurasia and one of the most water-rich rivers in the world. On a global scale, the Yangtze ranks third in terms of discharge and fourth in length. It alone traverses nearly one-fifth of China's territory, and approximately one-third of the country's population lives along its basin. Its delta, one of China's primary economic engines, contributes roughly 20% of the national gross domestic product. In this context, being connected to the Yangtze represents a considerable strategic advantage. Regions that lack such access actively seek to establish it both for passenger transport and freight. For Guizhou, this connection is made possible precisely through the Wu River and the infrastructure that renders it navigable despite a hostile terrain. The Goupitan Dam and its ship elevator system are designed to handle an annual volume of up to nearly 2.9 billion tons of goods. Certainly, it is always possible to transport goods by road or rail, but these solutions are far less efficient in a mountainous region. A standard truck can carry on average between 22 and 25 tons of freight. Even if one takes an intermediate value of 23 tons, dozens of trucks would be required to replace a single barge capable of carrying 500 tons, without even approaching the system's maximum capacity. In Guizhou, the construction of wide highways is often difficult if not impossible. Roads wind between mountains, bridges are narrow, and slopes are steep. Heavy traffic is slow, costly, and risky. Rail transport, although more efficient than road transport, remains constrained by the difficulty of laying tracks in such rugged terrain. River navigation, by contrast, offers a solution that is both safer and far more energy efficient. Barges consume significantly less fuel per ton transported than trucks or trains, within a framework of sustainable development and emissions reduction. This advantage becomes decisive. Thus, despite the technical challenges and high costs of ship elevators, the Goupitan system represents the most rational solution for ensuring both energy development and the logistical integration of a mountainous region at the heart of China's economy. A system capable of lifting ships weighing up to 1,800 tons already constitutes a remarkable achievement. Yet in China, this figure does not represent the absolute record. That distinction belongs to another giant of hydraulic engineering, the Three Gorges Dam. The ship elevator at the Three Gorges Dam was designed for far heavier loads. It is capable of lifting vessels weighing up to approximately 3,000 tons, almost double the maximum capacity of the Goupitan system. To achieve this, engineers designed a lifting chamber of colossal dimensions, nearly 400 feet long and about 60 feet wide. The volume of water contained in this basin is equivalent to that of 4 Olympic-sized swimming pools. Such a mass obviously cannot be moved quickly. Unlike the multiple elevators at Goupitan, the Three Gorges system relies on a single lifting mechanism. It takes approximately 40 minutes to raise a ship to a height of 371 feet above its initial level. Although this duration is longer, it must be considered in light of the exceptional scale of both the load and the height involved. Safety was an absolute priority in the design of this elevator. The system is equipped with 4 sets of drive mechanisms arranged symmetrically, which rigidly support the lifting chamber at 4 distinct points. This configuration reduces tilting and water sloshing within the basin, while also limiting the risk of destabilizing the vessel. Engineers also incorporated specific devices to handle emergency situations, particularly earthquakes. Damping and vibration dissipation mechanisms allow seismic forces to be transmitted to the supporting structures, thereby preventing the lifting chamber from falling or overturning. Operational results confirm the effectiveness of the system. Since entering service, the elevator has contributed to a significant increase in river traffic. In the first half of 2023, the navigation throughput at the Three Gorges Dam reached approximately 84.15 million tons, representing an increase of more than 9% compared to the previous year, a historic record. Before the ship elevator at the Three Gorges Dam entered service river, navigation was already possible thanks to another remarkable engineering achievement, a vast multi-level lock system. On both sides of the dam, 2 parallel sets of locks were constructed, each consisting of 5 successive chambers. For a vessel passing through the entire system requires approximately 4 hours. Each chamber measures about 280 meters in length, 34 meters in width, and 5 meters in depth, and can accommodate vessels weighing up to 10,000 tons. In theory, nearly all large inland vessels can pass through the dam using this system. Despite the lengthy transit time, the lock system remains extremely efficient. In 2022, the total volume of cargo transported through these locks reached approximately 159.5 million tons, a considerable figure on a global scale. However, the difference between 4 hours and 40 minutes is far from trivial. For shipping companies this time, saving translates into a significant reduction in operating costs and improved vessel turnover. At the national level, it has a direct impact on the fluidity of domestic trade. It is precisely this logic that justified the construction of a giant ship elevator as a complement to the existing lock system. China is not the only country to have devised original solutions for linking waterways separated by significant differences in elevation. In Scotland, for example, the Falkirk Wheel represents a unique structure in the world. Commissioned in 2002, it connects the Forth and Clyde Canal to the Union Canal, which were previously linked by a system of 11 locks that has since disappeared. Inspired simultaneously by a Celtic axe, a ship's propeller, and the rib cage of a whale, the Falkirk Wheel rises to a height of approximately 35 meters. It uses two balanced caissons, each containing around 300 tons of water. Thanks to the principle of displacement, the weight remains constant, allowing the entire system to operate with a surprisingly small amount of energy comparable to that required to boil a few electric kettles. This example demonstrates that ingenuity in vertical navigation is not exclusive to China. However, in terms of scale, capacity, and complexity, Chinese achievements remain unmatched. Navigating over mountains is no longer a metaphor or a poetic image. Thanks to modern engineering, this idea has become a concrete reality embodied by ship elevators capable of lifting thousands of tons of steel and water to heights once considered unimaginable. What seemed to defy the laws of nature is now integrated into the daily operation of China's inland waterways. The Goupitan and Three Gorges systems are not mere technical curiosities. They embody a broader philosophy that of a country determined to transform geographical constraints into strategic advantages. Where mountains once made transportation difficult or impossible, China has built navigable corridors. Where rivers once disrupted the continuity of traffic, it has invented solutions capable of reconciling energy production with river logistics. These infrastructures also illustrate a clear energy ambition. By intensively exploiting the hydropower potential of mountainous regions, such as Guizhou, China, is strengthening its transition toward renewable energy sources while maintaining efficient, resource-efficient transport networks. In a country of this scale, every gain in efficiency is multiplied at the national level. Beyond the numbers, the heights, and the tonnages, these structures tell a deeper story, that of humanity's ability to reshape the landscape in order to meet complex economic, energy, and social needs. Watching a ship rise silently above the mountains carried by cables and steel structures is witnessing a spectacular encounter between nature and human determination. Thus, in the steep valleys of southwestern China, navigation has conquered the third dimension. Ships no longer merely follow rivers, they now cross mountains.